This is a particularly difficult related rates problem. I love assigning this problem because it's such a challenge to set up. The derivatives, after you get the equation set up, the derivatives are really easy. The problem is figuring out what to take the derivative of. So you've got a swimming pool and it's filling with water, and you need to find out how fast the water level is rising when the depth is 5 feet, right? The water level is going up, and based on the shape of the pool, you can imagine that the water level goes up really quickly at first, more quickly, and it slows down and it slows down and it slows down. And here, after it gets to 6 feet deep, probably the water level goes up at a constant rate, but not down here. So actually this picture is pretty accurate, right? The deepest point is 5 feet. This part of the pool is 6 feet deep, and they're showing the water level being like right here. That's probably 5 feet. So I feel like this picture is pretty accurate. So I need to find out how fast the water level is rising. That means that the water level needs a name. It needs a variable. I like L. So L is going to be the depth of the water level. And what I'm looking for is dl dt. And I need to know what dl dt is when L is equal to 5. Now be careful. L equals 5, that's something that's changing all the time, right? The whole premise of this problem is that the water level is increasing. So we are not going to use L equals 5 until the very end. We're looking for dl dt. What do we know? We know about dv dt, right? It says the pool is being filled at a constant rate. That means that the volume of water in the pool is increasing at a constant rate of 0.8 cubic feet per minute. So that's a thing I know, dv dt, 0.8 all day long. And of course, I should declare what my variables are. Capital V, volume. So okay, here are my knowns. I have dv dt is 0.8, L is 5, but changing, be careful with that, and I've marked what L is. So now I gotta model the volume of the swimming pool, and I think that's the most challenging part. So here's where I started with in my brain. The volume is 20 times the area of the cross-section that's filled with water. So I want you to imagine, when I say cross-section, it's the blue part, right? So the area of that cross-section is actually going to be going up all the time as the water gets deeper. But it says right here at the beginning of the problem that the swimming pool is 20 feet wide all day long. So volume, length times width times height, right? So that's why I have this 20 here. So that's great. And now my challenge is to figure out what the area of this cross-section is. So here is the secret. The secret is to see this as a triangle, a rectangle, and that is going to be a rectangle like that, and a second triangle over here, okay? We are going to add up the areas of those three shapes to get the area of our cross-section. So here I go. The first area is actually pretty easy because this guy right here is a right triangle where both the height and the width are both L, right? Because this is like a 45, 45, 90. And so what that means is the area is 1/2 times base times height, 1/2 times L times L. Moving on. This guy right here is a rectangle. The base of that rectangle is going to be 12 feet all the time, but the height of the rectangle is going to change. It's going to be L. So I'm going to add 12 times L. Thirdly, and this part's a little tough, I have here a triangle that I need to know its area of. I know that this edge right here is L, but I'm not exactly sure what this is. So I drew myself a little sketch to make sure that I got my math right. I have this triangle, and I want to know the length of that top edge, but it is similar to this other triangle. So if the depth of the water were 6 feet, it would make a triangle which is 16 feet wide. I got that number right here. And then the vertical edge would be 6. I got that number right here. And you know what to do with similar triangles. We're looking for that horizontal edge there. And so I set up a ratio, 16 over 6 equals over L. And so that horizontal edge there is 8/3 times L. And that means that the area of the triangle is 1/2 times base times height. I'm stoked. I am ready to simplify and then take a derivative. To simplify, I'm going to distribute that 20, combine my L's into L squareds, all kinds of jazz. So I have 20 times 1/2, that's 10. I have L times L, that's L squared. I have 20 times 12 is 240, so there's my 240L. 80 thirds, right? So 20 times a half, that's 10. Multiply that by 8 thirds, that's 80 thirds. And then I have the 2 L's, that's L squared. I'm even going to push even further. 10 plus 80 thirds is 110 over 3. So V equals 110 over 3 L squared plus 240 times L. Now, I'm actually going to leave you to finish this problem. You need to use implicit differentiation. You're actually going to be taking ddt of both sides. So on the left, it'll be dv dt, and on the right, you'll get something else. And then use the quantities that you know to find out what dl dt should be.